Welcome to the deep dive. Today, we're cutting straight through the noise. We're bringing you some really specialized intelligence from just one critical institution, the National Center of Excellence in Analytical Chemistry. You might know it as NCEAC.
Right.
It's based at the University of Sindh, Jamshoro in Pakistan.
And this isn't just, a quick look at some papers. Our mission here is to give you the ultimate shortcut. We're pulling out and synthesizing the key insights, looking at how the faculty there are really pushing the boundaries in chemical sciences.
Yeah, redefining them almost.
Definitely. They're working on solutions that genuinely matter on a global scale. Things like clean water, sustainable energy, pharmaceuticals. It's happening right now.
That's the goal. And when we call NCEAC a premier institution, we mean it's more than just a lab. It's really an integrated hub. It combines top-tier scientific research, high-level education, and focused innovation.
It's where today's big problems meet tomorrow's analytical solutions, essentially.
Exactly. So to really get a handle on the scope, I think we need to start at the top, right?
Makes sense.
The center's director is Professor Dr. Amber Rahana Salangi. And this role, it's clearly not just administrative.
Oh, absolutely not. It's the scientific and strategic compass for the whole place.
And that compass is, I imagine, vital, especially in such a specialized field like analytical chemistry.
It's essential. Professor Dr. Salangi's leadership, it ensures the center stays excellent by constantly pushing for innovation. She maintains really rigorous academic standards, sure, but maybe even more crucial is how she fosters international collaboration. That's what keeps NCEAC's work relevant globally,
So she's kind of translating these big global challenges into actual research goals for her team there.
Precisely. It seems like the director's main job is ensuring the output, whether it's papers, patents, or even the graduates, meets the absolute highest standard.
The highest caliber.
Yes. Her vision really dictates the whole operational strategy. It focuses the faculty's diverse talents onto specific high-impact areas, and we see that focus reflected very clearly in their research matrix, which I think we're getting into.
Yeah.
That ability to pivot and focus, that's what makes a leading center stand out from just, say, a standard university department.
Okay, let's unpack this then. We've got 9 key faculty members, 9 brilliant minds working here. And their research, it isn't just scattered all over the place. It seems to form this cohesive ecosystem.
That's a good way to put it, yeah, a scientific ecosystem.
Designed to tackle major industrial and environmental problems, things facing the region, but also the wider world. So to help us, and you listening, process all this specialized work, we've grouped it into 3 integrated themes. Okay, theme A. This one really addresses a fundamental need, cleaning up our environment.
Quite a few faculty members are focused specifically on using analytical chemistry as a tool for, environmental repair.
Right, makes sense. We can start with Prof. Dr. Najma Memon. Her focus is heavy on environmental and food analysis. She uses advanced chromatography. That's the technique for separating mixtures, right?
That's the one, separating complex mixtures.
To improve water remediation. But what really caught my eye was her work on waste-to-value material conversion.
Ah, yes, that's fascinating. It's a pretty revolutionary concept, actually. It means taking stuff we normally throw away, industrial residues, agricultural waste like rice husks, maybe certain types of sludge, and chemically treating it, either to pull out valuable components or even convert the whole thing into high-grade, specialized materials.
Like what kind of materials?
Things like advanced coatings or precursors for fuel. It literally turns a disposal problem, a liability, into an asset.
Wow. That sustainability angle is obviously a huge driver here, and Dr. Jamil Ahmed Beg's work seems to echo this. His focus is explicitly on environmental chemistry, especially water and soil contamination, and he's developing eco-friendly ways to clean it up, often involving nanoparticle synthesis.
Right. Dr. Baggy uses these incredibly tiny nanoparticles, almost like highly efficient cleanup crews. Because they have such a massive surface area relative to their size, they can soak up pollutants, maybe dyes from industry or pesticides. Or they can chemically neutralize them much, much faster than older methods. It's really targeted cleanup right down at the molecular level.
And you can't fix what you can't measure accurately. That brings us neatly to Dr. Hassan Imran Afridi.
Yes, precision measurement.
His specialty. Heavy metal analysis, environmental monitoring, developing new analytical methods, particularly for detecting things at trace levels.
And in analytical chemistry, trace detection is, it's the gold standard. We're talking parts per billion. sometimes even parts per trillion.
Incredibly small amounts.
Exactly. So if a water standard says you can only have, say, 1 part per billion of lead, Dr. Afridi's work ensures they have methods sensitive enough to measure that accurately. That kind of precision underpins all environmental rules, all public health safety checks.
Makes sense. And finally, in this first theme, we have Dr. Amna Baluch. She seems to bridge material science and environmental cleanup, using nanomaterials, catalysis, and something called imprinted polymers for remediation.
Ah, the molecularly imprinted polymers, or MIPs. Yeah, let's quickly define that because it's really clever stuff. Imagine creating a very specific lock and key, but at the molecular level. Dr. Baluch creates a synthetic polymer, like a plastic, that has these tiny molds or cavities.
Okay.
And these molds are specifically shaped to fit only one target pollutant molecule, let's say arsenic or maybe cadmium. So when this polymer material is put into contaminated water, it acts like a kind of super efficient molecular sponge.
Wow.
It just pulls out that specific target molecule it was designed for with incredible precision. It's like custom chemistry for cleaning up specific pollutants.
Okay, so if we connect the dots here between theme A and theme B,
Yeah.
it seems clear that a lot of the research relies on creating these very advanced materials first, right? To solve the cleanup problems. This is where nanotechnology really looks like the backbone of the center's whole strategy.
It really is. And what's fascinating in theme B is seeing how these materials get translated. They move from being cleanup tools to being used in really sophisticated applications like in health and energy.
Right.
And we see Professor Dr. Solangi, the director, actually doing active research here too. She focuses on nanomaterials, sensors, and biocatalysis that's using enzymes to drive reactions. But also, interestingly, specifically on agrochemical delivery systems.
Agrochemical delivery systems. Okay, that means making sure things like pesticides or fertilizers get exactly where they need to go.
Yes.
Without loads of runoff and waste.
Precisely. It boosts efficiency, so you need less chemical in the first place, and it dramatically cuts down on environmental pollution. So this application of nanomaterials, it tackles food security and environmental protection at the same time.
That's clever. Now, shifting towards maybe future industries, Dr. Huma Mudasar's work, this sounds like highly advanced materials science.
It is.
She's working with graphene-based materials, nanocomposites, membrane technologies, and the applications sound quite high stakes.
They are definitely core future technologies.
Uh-huh.
When she works on graphene materials, she's potentially creating components for next-gen sensors.
Faster, more sensitive sensors.
Exactly. Faster, more sensitive than what we have now. And her membrane technologies are crucial for really efficient separation processes. That could be in advanced fuel cells, for clean energy, or it could be in highly controlled drug delivery systems for pharma. This is very applied chemistry, aiming squarely at global health and energy challenges.
And speaking of sophisticated filtering, Dr. Ayaz Ali Memon, he's focused on using graphene oxide membranes specifically for ultra-efficient water purification.
Yes.
Alongside developing those molecularly imprinted polymers similar to Dr. Baluch and also spectrophotometric method development.
That focus on graphene oxide membranes is quite strategic.
Yeah.
Graphene oxide lets you create these tiny, very controlled pores that can filter out impurities right down to the size of just a few molecules.
It's incredible.
This is how NCEAC is aiming to design filtration methods that could use way less energy and need less complex infrastructure than traditional methods, which could make clean drinking water access, actually viable even in remote places or areas without many resources. Okay, our final theme, theme C, is really the essential foundation for everything else. It's about developing the analytical methods themselves, making them rapid, accurate, and sustainable. These methods feed into both the environmental work and the industrial applications we've talked about.
Right. This is where speed and accuracy meet real-world relevance, especially for industry. Professor Dr. Faranaz Telpour, she specializes in lipid chemistry, the science of fats and oils.
That's right, lipids, and also enzyme immobilization. She's described as a master of fast analytical techniques, using them for both food quality analysis and environmental safety checks, including trace metals.
Enzyme immobilization. What does that involve?
It means fixing enzymes, the biological catalysts, onto some kind of solid surface. This way they can be used over and over again for tests.
Ah, makes sense. Cheaper and faster.
Exactly.
Yeah.
Makes analytical tests cheaper and quicker. So when she uses fast techniques for food, she's getting quick results on things like freshness or detecting if cooking oils have been adulterated,
Why?
or confirming nutritional content without waiting days for lab results.
Vital for quality control, supply chains. I can see that.
Mm-hmm.
And then kind of bringing us full circle back into sustainability, we have Dr. Sarfaraz Ahmed Mahesar. He focuses heavily on oils and fats too, but also on converting oils into biodiesel and advanced analytical method development, specifically using techniques like FTIR.
Yes, FTIR, Fourier Transform Infrared Spectroscopy. It's a really powerful technique that lets you quickly identify the chemical structure of materials.
Right.
Dr. Mahesar uses it not just to check the quality and purity of oils and fats, which is crucial for food and pharma,
Right.
but also to monitor how efficiently the biodiesel production process is working and check the quality of the final fuel. So he's directly linking fundamental chemistry with the sustainable energy sector. It's a great example of that integration.
It really does highlight how integrated NCEAC seems to be. You've got researchers making nanoparticles,
Mm-hmm.
designing specialized filters, measuring tiny trace elements, and making sure the final product, whether that's clean water or pharma-grade oil, is safe and actually works.
Yeah.
It feels like a joined-up scientific assault on some key global problems.
So all this amazing cutting-edge research is happening. But what about the next generation? What does it mean for the students walking through NCEAC's doors? The faculty are researchers, obviously, but they're also educators, right? That's a critical part of the mission.
Absolutely. That educational imperative is what transforms NCEAC from just a research lab into, well, a talent incubator. The students there, the MPhil and PhD scholars, they aren't just sitting in lectures learning chemistry theory. They were right there, embedded in these groundbreaking projects we've been discussing.
So it's less theoretical instruction and more like an apprenticeship in innovation. Are students really working directly on, say, waste-to-value projects or these advanced materials?
Mm-hmm.
They absolutely are. The faculty, collectively, put a massive amount of effort into mentoring these scholars, supervising their thesis projects, organizing seminars on the latest techniques. It's very hands-on.
Mm-hmm.
This approach ensures the curriculum is always centered around the newest discoveries, often their own discoveries. Students are directly contributing, maybe helping develop those graphene oxide membranes for water purification, or designing the next batch of molecularly imprinted polymers.
That must make a fundamental difference to the outcome. Graduates aren't just leaving with a degree. They're leaving with, potentially, solutions they helped develop, maybe even patented.
That is the key difference, I think. The combined expertise of the faculty ensures students get deep theoretical knowledge, yes, but it's coupled with invaluable practical lab experience. They're using high-tech equipment, daily advanced chromatography systems, FTIR units, things like that.
Yeah.
So NCEAC graduates, they're not just standard chemists. They are trained innovators. They're ready to tackle complex industrial, health, and environmental challenges anywhere in the world.
Right.
They're really prepared to create the solutions, not just identify problems in a textbook. #outro.
Wow. What we've really seen in this deep dive is just a stunning picture of focused scientific dedication. The faculty at NCEAC, working under Prof. Dr. Solangi's direction, they are actively pushing the limits of analytical chemistry and developing real, tangible solutions that impact our planet's health, our energy needs, industrial sustainability. It's quite something.
It really is a dynamic institution. And if you, listening, are curious to explore more, maybe the specific papers or opportunities related to the work of these 9 researchers, from agrochemical delivery to those fast analytical techniques, you should definitely check out their official resources.
Where can people find that?
The website is www.cacu.edu.pk. That's ceacsu.edu.pk.
Okay, great. That's excellent context for our listeners to follow up on. www.cscsu.edu.pk.
All right. And before we wrap up, maybe just a final thought for you to ponder, based on this integrated strategy we've just walked through. Given the really intense focus we saw at NCEAC on both environmental remediation and advanced materials, especially where water purification techniques meet new energy applications like fuel cells,
Yeah.
which specific area, in your view, seems strategically poised to deliver the most immediate, globally recognized breakthrough for Pakistan in, say, the next 5 years?
Yeah.
Is it going to be cheap, readily available drinking water via things like graphene membranes, or maybe the creation of sustainable energy components? It's a really compelling future, and it all seems to hinge on that analytical precision they're developing.
That is a phenomenal question to close on. A lot to think about there. Thank you for diving deep with us today.
My pleasure.
We will catch you next time.